Well, it looks like we can get started. Welcome back, everyone. Well, the folks that made it in today, looks like it's a pretty light class. It didn't help taking off the Tuesday class due to illness. Probably should have made another email to say class is on Thursday. But the good news is all these lectures are going to be recorded, so that's one way to participate for sure. I have several comments on here. Don't want to read them out line by line, but the major thing I want to point out is, as far as the due dates go in WebAssign, they're always going to be due 1 week after we finish a section. So for section 2.2 in WebAssign, the due date is going to be, looks like January the 30th. Also, those due dates are posted pretty clearly once you log into the WebAssign system. So that's a good thing to double check each time you're looking into the course, where you're at and that kind of stuff. Aside from the WebAssign homework, that's where you're going to spend most of your time working on the course materials, but there'll also be weekly quizzes. Idea with these are, this is your opportunity to do a problem that's going to look a lot like a real exam problem. There won't be as much of a disconnect that way if all you're doing is WebAssign and then you suddenly have to do a paper exam. So this is a way to bridge the gap between all of your work in WebAssign and what you're actually going to be doing on paper. They're meant to be really short and sweet. The way to actually access one is just click on this PDF right here. And should have had that set to auto display. I'll fix that later. The quiz is just this PDF file here after you click on the quiz link. And this is the problem that we'd be working on in our first quiz. Pretty much the same kind of stuff that we've been working on the prior days. We're going to calculate two limits based off the graph here, and then state the equations of the horizontal asymptotes. So again, when you work these kind of problems, think of this as an exam one dress rehearsal, basically. If these ideas seem really foggy, then this is your opportunity to get extra help, because this is my way of saying this is a concept you need to be ready to go on for the purpose of exam one. So again, if any quiz just seems like it's kind of vague, you're not sure how to start, where to get going, or if you're not even sure if your answer is what is expected, these are just meant to be extra homework. I call them quizzes just so that they feel different from WebAssign, but you can get help on these with me, whether after class, before class, during office hours, or even just over email, if that works best. Due dates on quizzes are very similar to the due dates on the WebAssign. They're going to be always posted. Let me fix this. Hang on. There we go. They're always going to be posted either on a Wednesday or a Thursday. If I posted on Thursday morning, probably just means I'm behind and trying to get caught up. But the due dates are always going to be on the following Thursday. So 1 week turnaround once it's officially posted. Well, I said that weird. It's always going to be due on Thursday after we come to class. It's officially assigned. Well, any last questions, folks, on either the WebAssign material or the week by week quizzes? Okay, now that we're talking about homework, I guess I have a question for the class. Any questions about, or any concerns, any problems coming up about either opening up the textbook to do the readings indicated here, or working on WebAssign, submitting answers, those kind of things? Have folks had any challenges, or things going okay so far? Awesome. I've got the thumbs up in class. How about for folks over in Zoom? Any issues at the moment? Sounds like we're pretty good over in Zoom as well. So let's get started with our work today then. We're on example 3, about to finish off the section 2.2 notes. And section 2.3, it's similar to what we did on this section, except we're not saying limit as x goes to infinity. We're saying limit as x goes to 5, for example. So that's what we mean by limits of functions at finite numbers. This is actually going to be split across two different sections. In section 2.3, we're just looking at the graphs and understanding the definitions. In section 2.4, we're going to be using the actual limit laws that came from here for the finite values. So let's get started by squaring away section 2.2. And this is where we left off before we went to the weekend last week. This is a pretty vague looking theorem. It just supplies us with 4 different limits. That's really challenging to try to remember all of these, Pat. So the reason for all this white space down below is each time you see something like this, it's a good idea to just consider the graph of the function you're working on. Everything here says e to the x, so let's begin by just saying f of x equals e to the x is the base e, because of the base right there, exponential function. E is just like a number such as pi, square root of 2. It's an irrational number. It's about 2.7. And in any calculator with its money that you purchase for it should give you that value. Just type in E, and that's its approximate figure. Sometimes this is referred to as Euler's number by the person who discovered and worked with this quantity here. So when we're taking all these limits, we're dealing with the function f of x equals e to the x. But notice this one has a transformation. That's e to the power negative x here and here as well. So there's really two functions we need to work on. Let's put them both on a common set of axes. So both functions are going to intersect right here at this point. And let's just color code this whole thing as blue. That might be helpful. For this function with the base c exponential and just x up here, not negative x, this graph would look about like this. Due to it being exponential, we expect rapid growth when x is larger than 1. But if you go to the left, we have exponential decay happening. It's dampening down to the x-axis rather slowly. That means there's also a horizontal asymptote. It runs through the entire x-axis with the equation y equals 0. So that's one function down. Let's put in the next one. Because we have power negative x here, we also have, let's call it g of x equals e to the power negative x. And this is really just a transformation of functions, depending on how foggy college algebra was or how recent it was. The idea is you swap x with negative x, that's just a reflection across the y-axis. So we take this blue curve, imagine you folded this paper across the y-axis, and this is the plot you would get. So e power negative x comes through in this way. And now we have two graphs, but 4 limits to consider. So let's run through the limits and see what's being really tried to express here through these graphs. Any questions at the moment plotting these? That one deserved a label. Okay, so let's take on first two limits. First one says limit as x goes off to negative infinity of e to the x. The claim is 0, but more importantly, we don't want to try to memorize all these things. Again, that's a hard way to learn this stuff. We should be looking at what the graph is and just resolving this limit through the properties of the graph. Because it says we're heading towards negative infinity, the first one I wrote down here, we're following this curve in that direction, and the limit will exist because there is in fact a horizontal asymptote, y equals 0. And that's what this curve is approaching. So the limit is 0, and it's coming from that information there. If we change it up, we'd be taking the limit as x goes to positive infinity of e to the x. Before we jump onto that one, any questions on the prior, the one that came out as limit 0? Okay, so next, we need to take this limit here. It says that we're taking x going towards positive infinity. So on the blue curve, you're following the red dot in this direction. But the values of these numbers are not settling down to anything finite. It's just getting larger and larger without bound. The further right you move x, the higher the red dot is going to go. I moved it about this far. It's off the monitor screen. It's just way up there now. That's why we put infinity on this one, because e to the x just grows without bound. It means the limit does not exist. And this is just a way of saying it failed to exist. The values are getting larger and larger without bound. Only because we're going off to positive infinity, so this direction. So we want to do it again for the next two limits with the e negative x on this one and this one. Let's write them in. So limit x goes to, I'll do the negative infinity first. Parallelism is always a good idea with this stuff to just make it easier on the mind. Limit as x goes to positive infinity, down below like before, with e to the x. And let's think about these carefully and see what we have. We're going towards negative infinity. Any volunteers for what the value of this limit ought to be? Turns out it wouldn't be zero on this one. The trick is we have to consider the direction. This tells us which direction we're going on the actual green graph for this one. Anyone see what the value should be? Sorry, say again. Correct. This one is going to come out as infinity, only because of the direction. When you read a limit, you always want to read that part first. It says x is going to the left in a roundabout way. So go on the blue curve. You're heading off this direction, but that means it's just shooting upwards now towards positive infinity. So we put an infinity right on that one, which is matching what this is saying. But again, this is really confusing if that's all they're giving you. You really want to connect that with the graph because now you have something to anchor in your mind why that is a valid limit. Well, any questions, folks, with that one there? Okay, another way to see this instead of using a static graph is these graphing calculators are a really great tool for checking our intuition on the limit. So you could plug in, say, y equals, oh, hang on, let me double check what I've written here. I should have put a negative x on this one. Sorry, folks. I put e to the x here, e to the x here. I think I was writing that a little too fast. Should have been negative x to copy that function and those limits there. Weird omission, sorry about that. But if we put the negative x, this is the point at which I noticed that omission, e power negative x. This is the graph we get. For following this, that means you want to click a dot here and just move it off to the left. If the second coordinate becomes some finite number, say it's getting closer and closer to 5, we'd say the limit's 5, but it's going to shoot past any finite number you give me just by making x sufficiently large negative. So at -2, we're all the way up to roughly 7.69. We can get over 70 just by making it, say, e power negative, let's put in 100. Well, that's a humongous number, e power -10. Negative of -10, that would be the right value to put in. Gets us over 22,000. We put in 100 there. We're already at a gigantic exponential function. Order magnitude 43 on that. All this to say is the function's growing rapidly as you head to the left towards positive infinity. But how about this one, the one down below? Anyone see the value for this limit? Absolutely. In class, folks are saying 0. So really all we're going now is in this direction towards the right. Value of the limit is the horizontal asymptote of 0. So let's connect that as well, highlighting. At that stage, the information down below is still saying the same thing as all of this, but this is also an explanation at the same time. We're really just using the properties of the graph and its horizontal asymptote to get these 4 limits to come out. Next problems, we're going to work with these limits and see what kind of exciting applications they could get involved in. Then we'll turn into the next section, 2.3. Well, any questions at all, folks, before we go to the next page? Okay, well, here's that next page. We have a couple limits to resolve, taking the limit of this kind of a mess right here. But then down below, we'll do an application. Looks like this one has something to do with the Pacific halibut fishing industry. But first, this will be a nice fun one before we take on the application. Just says find the limits, just like an example 2. In this section, we're either heading towards positive infinity or negative infinity. But we have to keep in mind that absolutely is going to affect your e to the x's, or if it's an e negative x. So this is a tough limit to start off right away. But actually, the way to solve this limit is highly similar to example 2. We go to the denominator and look for the thing that grows the most. 8 is constant, so it doesn't change at all depending on the value of x. But that thing right there is influencing the denominator the most, the exponential function. So we take that quantity, and we're going to divide all terms, numerator and denominator, by e to the x and just see what happens. Which, if we scroll up for just one moment, is exactly what we were doing on all these problems right here. We were going to the denominator, looking for the part which was the most influential, and then dividing all terms, numerator and denominator, by that quantity. So even though you can do these problems really fast as analyzing that horizontal asymptote, that technique has lots of applications on this one as well. But As we said before, if you look at this really closely, you might notice there is a shortcut to even on this one. Let's take this limit by first going, it's the limit as x goes to infinity. 17 is being divided by e to the x plus 3e to the x, also divided by e to the x. And rinse and repeat for the denominator as well. 8 over e to the x minus e to the x over e to the x. Okay, so like a lot of things in math, it gets ugly before it cleans up, but this is progress at this stage. We have some cancellations here and here that we can make. And we can also use properties of exponents on this one to do another kind of simplification. So this becomes the limit as x goes to infinity. I want to move the e to the x right where the red dot is, bring it up into the numerator. Algebraically, that's allowed, so long as you take this x right here and transform it to negative x. So in other words, the exponential property is that 1 over a base b to power of x is the same as base b to power negative x. For any base whatsoever, our base is e. So back over here, this turns into 17 e power negative x. Here we have a cancellation, so just plus 3. Down below, this is 8 times e power negative x. And here, another cancellation, just a minus 1. Highlighting these in green is just to remind us what happened in the last set of notes. Let me see if we can scroll up there and just take something out real quick. On the graphs we were analyzing, we like the e to the x when it has a power negative x and we're going to infinity, because those are all going to turn into 0. So this is really a 17 times 0 right here, an 8 times 0 when we take the limit as x goes to infinity. And now we're left with 17 times 0 plus 3, 8 times 0 minus 1. If you just wrote this as 3 divided by negative 1, that'd be totally fine as well. I would just take that to mean you knew these parts went to 0, and so they're gone on the next step. The limit is now just negative 3 on this one. Let me just box that out. Well, we did, folks. I think this is a kind of a tricky limit to look at. But just like before, notice what kind of happened. We had a 3 here, a negative 1 times e to the x here, and that's what it resolves to, 3 divided by negative 1, just as if this was an x squared and an x squared here. Well, that's one down, our first big problem of the day. Any questions whatsoever before we try the application? Okay, so here's our application for this section. I'm going to try to put an application on each one of our set of notes because that is a big part of this course. There won't always be a direct application that matches it up in the homework. Sometimes it's hard to get the homework system to give a good application. I think we do have one in section 2.2 that's pretty similar to this. So solving that one is going to be a lot similar to what we're doing in these notes. We're told the Pacific halibut fishery has been modeled by this equation. So B of T is all of that. This is a population growth model. And here, the thing that we're modeling is B of T, which is the biomass in kilograms of the halibut in this fishery at time T. Probably T is measured in months, days, something along those lines. So this is going to be the biomass at any time T. We have to calculate the limit as T goes to infinity. But the bigger challenge in this class is after you calculate something like that, we can't say what it means, then it's almost useless, right? This is actually the hard part of this problem. We'll have to say what the significance of the limit is using the context above. So let's give it a try. First, we'll just take on the limit. Let me copy it down here. Is the limit as time goes off to infinity of B of T. It's a weird quantity to calculate because, well, the Pacific halibut fishery is not going to last for all of time. And this is saying time going off to infinity. What we're really trying to just say is what's going to happen to the biomass of your halibut fishery in the long run when we say T goes to infinity. what's happening to the model in the very long run, or what is the horizontal asymptote of that function is essentially what we're trying to ask. So we'll take the limit as t goes to infinity. Let's just plug in the function, 8 times 10 power 7, divide by 1 plus 3, e to the power of negative 0.7t. Okay, so we have a common limit like we've seen before, just like on the last problem. Let me carry that down just once more for easy reference. And so we should expect that this formula should work, just like before in the last problem, to resolve this limit right here. We would expect this becomes 3 times 0. There might be kind of a small little hiccup on this. Anyone see a problem with the formula versus what we have here? If no one's too concerned, I think that's kind of great. This formula does in fact work on this one. But the one thing that might seem weird at first is, notice this is just e negative x, or negative t if you change the variable. And this is negative 0.7t. It kind of feels like a different function. But loads of things you can do with this. One of it is you can rewrite e power negative 0.7t as e to the power of negative t to the power of 0.7. In the exponent laws, the exponent of 0.7 would multiply the exponent of the negative t. Then when you go to take the limit, you're just influencing the inner part of this function right here. So that's one way to think about what's happening to this function. Or another still, in Desmos, you can observe that just about any value you put in here, like 0.3, is going to have the same feature. As t goes off to infinity, the limit is always going to be 0. No matter what constant I put on here, it just has to be a negative value. So even a negative 0.003, it's just going to take a little while, but those values are shrinking down. So either way we look at it, that part goes to 0, and we get 8 times 10 power 7, 1 plus 3 times 0 upon taking the limit. Here, notice we drop the limit statement in front, only because now the limit has been taken. There's no other value that's being influenced by t. So this just becomes 8 times 10 power 7 kilograms for the biomass of those Pacific halibut. So the limit's done. All we have to do is say, what is the significance of this value right here, now that we've calculated it? Any questions at all, though, in actually getting this value? Okay, so here's the hardest part of this problem. We now need to say what this means. Best way to do these kinds of problems where you're giving an interpretation to the quantity that you've just calculated is, it's kind of like a bit of role playing. Imagine you are the owner of this Pacific halibut fishery. Your main concerns are how much revenue you're going to get out of it, what is the maximum biomass you could ever get in this halibut fishery. As time goes on, we expect the biomass to increase, and the limit says it increases up to this amount. So this is the maximum amount of biomass your halibut fishery could ever obtain. And now you have a sense of what the revenue might be year after year if this is the maximum value. We need to write down a statement that follows that. So let's see if we can say something a little bit more brief. Let's say, from that part right here, in the long run, only because time was going to infinity, this is a great way to convey it when we're just saying this value in ordinary words. In the long run, the biomass of, you could say, the Pacific halibut in this fishery, or I'll just say the biomass of these fish. It's okay to be a little bit terse with the context and just summarize it to that part. We already know when we say these fish, we're referring to these ones. So the biomass of these fish gets closer and closer to 8 times 10 to the power of 7 kilograms. So that's what this model is saying here. If we take the limit as we go to infinity, once we actually work with the Pacific halibut in this fishery, in practice, it might exceed this or it may never get to this value. Keep in mind, this is just a model. It's just a mathematical way to try to approximate reality. And the accuracy of this model is going to influence the accuracy of this statement. But if this is the best tool we have to make a prediction and you really own this fishery, there's a lot of value in doing that limit to think about best cases and worst cases in this kind of business. But we did, folks. That's one application to these kinds of limits. In the next section, the only thing we're changing is saying, instead of saying t goes to infinity, we might say t goes to 5. Maybe that's 5 months of operation of this fishery from the start to that point in time. But before we get to that, into that next section, any last questions at all, folks, about 2.2?
Yeah, I have a quick question.
Yeah, go ahead.
The 8, and then so you got the 8 times 10 to the 7th power. Would we just want to get that to a number, or do you want it left like you have it there?
I would say that's more of a stylistic choice. I'd go with whatever makes the most sense. As far as the homework system WebAssign goes, it would take the number in either format.
Okay, perfect. Thank you.
Yep, you betcha. I think most science classes would probably expect scientific notation, but I'm not going to be too picky about your values. As long as they're accurate, I'm happy with them. Other questions so far? Okay, let's save this up. Takes a minute for this Word document to actually save. And now for our next section, we're going to be in 2.3, limits of functions now at finite numbers. Again, we're going to see this a couple different ways. 2.3 is going to be mostly a qualitative assessment or analysis of these kinds of limits. But that's a great way to absorb this information, of which there is, just like in the last section, quite a bit to get our hands on. So let's start off with this new limit. Again, the major feature is just by the red dot. We're setting x towards a number, not a positive infinity, not a negative infinity. That value a could be 5, it could be 8 times 10 to the power 7, something like that. But it has to be an actual finite number. So if we have f of x is defined when x is near the number a, so there's going to be a domain that contains contains number around a, but it doesn't actually have to include a. So just like this function right here, think of the one down below as the a in the problem. This dot right here says that f of 1 is 1, but that could be removed entirely, and we can still take on this limit. The limit says, as x goes to a, the values of the function f of x will be getting closer and closer to a value of L. So if we can make the values of f of x close to L, as close as to we like, by taking x sufficiently close to a, then that limit exists and comes out as L. But that statement right there is actually really, really important. It turns out from this statement that the limit as x tends towards a of f of x equals L is not affected by the value f of a. And this is the weirdest thing about these kinds of limits. It's the reason we did this set of limits a little bit last. I think they're quite a lot trickier. So whatever happens at a is totally irrelevant. The function could be undefined entirely, but we can still take that limit. And that's about what we're about to do. We're going to take the value of f of 1 as well as the limit of as x tends towards 1 of f of x. Actually, this is also just a great way to practice analyzing these kinds of graphs. We have to know what is even meant by the open circle versus the solid dot. So a lot of information is really being conveyed here. So let's go with first f of 1. To evaluate f of 1, all we do is we go to 1 on the graph on the x-axis, move either up or down until we hit a point on the curve, and there will be exactly 1 point since these graphs have to satisfy the vertical line test. So when we go up, we actually stop right here. That's the point of the graph. This is a hole in the graph. There is no function that sends us to 2 when we plug in 1. So f of 1 just outputs 1 on this graph through that value. So we're halfway done, folks. We have the function value. Any questions with this computation? Okay, here's the weird one next. Now we want to do the limit as x tends towards 1 of f of x. One thing we can do right away is use this comment right here, because whatever actually happens at f of 1 is totally irrelevant to the limit. That's the weirdest thing about this. So let's use this tool right here just to emphasize. The value at 1 is totally irrelevant. So you can put like a little blinder through 1 and now evaluate the limit. We want to take x closer and closer to 1 and see what the function values are, the height of the curve in blue, as x gets closer and closer to that value. So on one hand, let's use this pen right here just to emphasize these values. As x tends towards 1, there's 2 directions you have to approach from. Either you're coming in from the left, all of these values are less than 1, or you're coming in from the right, all these values are greater than 1, and we hope the curve is heading towards the same common value. So here's one input. If x is tending towards 1, then this is pretty close. It looks like a 0.6. We go up, we hit the curve, and output some function value there. Now let's get really close in on this. Because the limit is heading towards 1, we can get as close to 1 as we'd like, except we can't plug 1 into this one. That's just doing the function value, not the limit. So we can get even closer, say right here. Go up, hit the curve, and notice as we got closer to 1, right where the red dot is, the function value is getting lower. It's dropping down ever closer to 2. If we attack it from the right-hand side, we need to see that same behavior. So let's take a value, maybe let's delete that so we can see a better picture here. Let's take a value even closer, say right here. This value will come up, hit in this location, and move to that value there. Actually, let me use a different color so we can see the difference between the right and left direction. So we're starting here, moving upwards, getting value. So it's between the other values. Let's zoom in just a little bit more, see if we can make this work out. Yeah, I've got the pen set as small as it can go. So now if I take a value right here, this is meant to be just to the right of 1, pretty much the best I can do without the limitations of the pixel width. We would go up through, hit that point. Notice we missed the hole. We'll never hit the hole because we're not putting 1 into this. We're just getting close to 1. So as we came out here, function value is even lower. It looks like the closer you plug in these values, the closer and closer you're getting to some number out here. That number we seem to be approaching is the value of the limit. And in this problem, there will be a value of 2 altogether. So that's one way to think about these limits. But I think, again, they're pretty tricky the first time you look at them. So that's why we're spending a little bit extra time in section 2.3, seeing them through the graphs, and then we'll try to get in 2.4 through the limit laws. Let me erase these so it doesn't look too crazy if you come back to these notes. But again, the overall idea here is that this is a decent idea when you go to evaluate these limits. Imagine that there is a blinder right here, because no information here matters whatsoever on this limit value. We're just wondering, what are the function values approaching as we come in from this side? With x is getting closer to 1, function values are getting lower, closer and closer to 2. From this side, x is getting closer and closer to 1, and function values are also dropping down, getting closer and closer to a height of 2. And so we say that is its limit. So this graph right here in example 1 just meant to introduce this new definition. We'll take a look at some more graphs and pick up more ideas as we go along the way in section 2.3. But any questions so far to that stage? Okay, well, let's try it out all over again then. On example 2, we're just kind of redoing the same kind of idea. But this time the difference is we have 3 different functions, f of x, g of x, and h of x. These are their real graphs plotted in every case. Notice the difference between the open dots, the open dot with a function value, and, well, this is the one with the actual dot filled in. The function value connects right here. Now, the other thing about graphing these functions is it's actually pretty tricky when you plug these into a graph. If you graph this one, let's call it f of x equals x squared minus 1 divided by x minus 1, and then compare the graphs we're looking at, seems like this graph is a lie, right? Unless you move close to 1, and the graph does produce a hole just like that. There's actually a disconnect, a discontinuity inside this graph where the function's undefined. But graphing calculators usually don't even show that dot, and it comes off the moment I lift the mouse clicker. So that's something that's really weird about these kinds of functions with technology. These graphs are literally plotted by connecting the dots, and it was connected through that hole in the graph, the discontinuity. But you know what? It doesn't matter. You can still calculate this limit, even if there's no function value there. We're going to show how to do this one just purely algebraically, so we're going to come back to this function. But in part A, we can just simply say the limit, we're taking the limit as x tends towards 1, so write x towards 1 under the limit statement of f of x equals, let's take a look. As you come in towards 1 from the left, function values are getting higher and higher, closer and closer to 2. They'll never actually hit 2, but that's okay. The value of the limit is the value you're getting approaching towards, whether or not you actually hit the value or not. Coming in from the upper end, the values are dropping, getting closer and closer to the same value of 2. So that tells us the limit on this one is 2 itself, despite the fact that f of 2 is, let me try again, f at 1, the 1 is the relevant part right there, is undefined. So the value of the limit does not depend in any way on the function values, what this part A is trying to convey. It could be defined, it could be undefined. It's irrelevant. This one has limit 2. Well, let's try this again. This function g of x feels complicated, but look what it's done. It's taken the f of x function right here, whose domain is all real numbers except x equals 1. So part A is just replotted right here. We had that f of 1 is undefined, but g of x defines it. It says g of 1 is 1 because of this information here, and that's what gives us this part of the graph. So that's a decent thing to connect. Let's highlight this portion of the piecewise definition corresponds to producing that to 1 point. Its whole effect is now g of 1 equals 1. Our goal is not to calculate g of 1. What we really want is the limit as x tends towards 1 of g of x. Any volunteers to say what this limit ought to be?
It's 2, right?
Yeah, good call on that one. Just like as before, if x gets closer and closer to 1, the second coordinates are always getting closer to 2. It doesn't matter which side you approach on. We're always lining up, getting closer and closer to 2 on either direction. So this one also has a limit of 2. And again, the idea here is whether the function is undefined or defined, totally irrelevant. The limit still just 2. And this one, h of x, is kind of strange in a way. Again, we're going to come back to the function f of x and h of x and say a lot more in section 2.4. But if you're curious what's going on is, if you factor this numerator, then cancel the x minus 1 up above and the x minus 1 down below, you get just x plus 1. But this function right here is not the same as this function. They differ at exactly 1 point. It filled in the hole in the graph, the discontinuity, and we can say here, the limit as x tends towards 1 of h of x. It's almost like we're just plugging a 1 right here and adding them up, getting a 2 out. You cannot do that here. You can't plug a 1 into this function because you would have divided by 0 in that attempt. Otherwise, instead of using just the algebraic form, it's the same idea. As you get closer and closer to 1 on the left, the height of the function is getting closer and closer to 2. And similarly, if we approach from the right. So either case, we have the values 2 here. And as before, we can say h of 1 is 2 as well. But these are the main results. And this is just the side comments that go right under it. So example 2 is pretty similar to some of the problems you're going to see in the real web assigned homework in section 2.3. And again, we're going to come back to these 3 graphs when we're in section 2.4 to show how to do that limit if no graph whatsoever is provided. But any questions at all, folks, on these 3? Okay, let's march on forward to the next concept here then. Here's the point at which I feel the notes get pretty vague. We have the same limit statements as before, but we're putting in some special subscripts. That's a with a, subscript, a superscript in the power position. You could read that as a to the power of a negative sign. That's not really what's being conveyed on this. This is saying we're taking the limit as x approaches a purely from the left. That's why we have a negative there. If there's a plus here, it means we're taking the limit as x approaches a coming in from the right-hand side. So sometimes these limits here are called single-sided limits for that reason. Let's just say that here. These are single-sided limits. Let's peek up above on the notes just for a moment. The limits up here are always considered double-sided, even if we fail to say it, because there's no superscript here that said plus or minus. And that's why each time we graphically analyze these limits, I mentioned we're coming in from the left and getting the same value as we come in from the right, because these imply 2 directions have to give you the same value. Down here, we're always picking a specific direction now. So let's put in a graph on the white space and see what's going on with these 2 brand new limits. So let's put in something about like this. Instead of putting in an a, let's put in a definite number in this position. How about 2? And instead of the limit L, let's put in some actual values on the y-axis. We've got 1, 2, 3 we'll be working on. The function f of x that we can plot in blue. And so this is my graph. So right at 2, I'm going to put an open circle here at height 1. At coordinates 2, 3, another open circle. And the curve is going to look like this. Comes in this interesting way, connects to this dot, but doesn't take on a function value. And it's diving down in that direction. But it continues from up here and just moves up in that direction. So now there's 2 interesting limits that we can calculate here. Right out of the gate, we can also say f of 2 is undefined. Let's start with this limit here, taking the limit as x tends towards a, coming in from the left. The a value again is this 2 we see right here. And the first limit to calculate is, let's take a look at limit as x approaches 2 from the left of f of x. So that directionality again is now really supremely important to us. It means we have to be trailing on this curve right here. We're wondering what is the function getting closer and closer to as we approach 2, but only from the left side getting closer to 2. And notice that matters the side you approach it on this function because the function values would be different. So as we approach from the left, the function value is getting closer and closer to a height of 1 on this one. So we will say equals 1. Does that make sense to folks on that first left side limit? Okay. Okay, so this whole part right here is for that limit there. So it's gonna look too crazy if we put in too much of that highlighting. Now let's try up this one up here. That's when we're taking the limit as x approaches from the right-hand side. So we can say lim, we want to approach 2, but only from the right-hand side. So a plus would go in right here of the same function f of x. So now in this one, because of the directionality, we pick the top curve. Let the first coordinate get closer and closer to 2, and observe the function values appear to be getting closer and closer to a height of 3 in this direction. So now the limit of this one is equal to 3. And at this stage, well, we've done it, folks. That's what we mean by single-side limits if we're approaching from the right or strictly from the left. Any questions at the moment with either of those two limits?
If the line was moving straight down towards 3, would you say negative infinity, or would you just keep that 3?
It would still be a 3, yeah. So you're saying if the curve went kind of like this.
Actually, no, I was thinking like if it's just going just straight like that.
Which direction? To the,
On your screen, it would be up to the right straight.
so like
yeah.
that?
Like I was thinking, yeah.
Yeah.
It looks like it's gonna keep going down forever. You wouldn't say negative.
You mean conveying it in that direction? Well, the trouble with going in that direction is then the curve would violate the vertical line test. We would have an intersection here and here. So we would have 2 functions instead of a single function. All the questions so far? Lots to say about this one for sure still. I guess the bigger question about this is, one purpose of single-side limits is to resolve what's happening to this limit as x approaches 2 of f of x. Now, this one is suddenly really different out of nowhere. It's the same one we've been looking at before, but there is no symbol above 2 in the superscript position. So that implies this one is a double-sided limit. If we attempted to put a value here, what would you say the best value is? It's a tough question in a way, right? Any volunteers for what feels right to put right here?
For this graph, wouldn't it be like it does not exist?
Absolutely good call on that one, Nick. If there is 2 competing values, well, that's a problem in mathematics. In mathematics, just like what we were mentioning with the vertical line test, we want one output the moment we define a new operator. Well, there is no one output. It depends on the direction you take. It's either 1 or 3. And so like you said, this is a case where we would say the limit does not exist, or DNA, DNE. That comes up so much in calculus classes that that's become the official shorthand. It's even used in WebAssign when the limit fails to exist. But we should always say what these acronyms mean as the moment they occur. So that stands for does not exist. And again, it fails to exist simply because the single-side limits didn't match up to the same value. Or in other words, you can tell it doesn't exist because of this jump in the graph, which we'll later call a jump discontinuity. If this curve came down here, if I could make it, go in just right, it's a little tough on Microsoft, then the limits would have existed. It would have been the same value. We came in from the left side or the right side. But written this way, we've broken the limit. It just purely doesn't exist. And that's the content of theorem 3. It says the limit as x tends towards a of f of x exists and equals L if and only if the single-side limits match up to the same exact value. So that was our problem in this example. Single-side limits were different, so the overall double-side limit did not exist. Well, we've got more tools about limits at our disposal. So we'll pause a little bit, do a typical kind of homework exercise, and then look into some more concepts. Don't think we'll finish this notes today. We're not trying to race through it. So we'll be probably finishing this when we come back on Tuesday's class. Any last questions at all, folks, on definition 2 or the related theorem 3 below? Okay, so far, this class is kind of interesting. In our calculus class, we're just analyzing loads and loads of graphs to start out. But again, in section 2.4, we'll see how to do all this kind of stuff when it's not a graph provided right here, but an actual function that's being given algebraically. But for the moment, this is a pretty similar set of exercises that you're going to see in the actual WebAssign homework. Only purpose for the graphs are, these limits are tough and technical, but if you can see how they work graphically, then it gives your brain an extra edge on doing these things analytically in the next section. So it says here, use the graph of f to state the value of each quantity if it exists. If it does not exist, we have to explain why, but these are always pretty brief explanations I'm going for. So I have a graph provided in this way. We have a solid dot, some open dots here and here. And this is all considered one curve, which some sure has some issues. It has breaks and such. But all of this is y equals f of x. All we're doing here is evaluating a couple limits. So let's start off on this one. It's the limit as x tends towards 2. Let me zoom in on that. Coming in from the left. Let's use this tool once again. Because it says 2 from the left, this is always the first thing you want to read in the limit. You want to go here where 2 is. Then grab something like this, like note card, maybe an extra window, something like, say, this if you're working on a computer. Let's just grab Notepad. Because the strategy here is, if you cover up a part of your graph, it really helps out the eyes on seeing on this limit. There's a lot of noise on this graph, but the idea here is covered up with your card, a hand, an extra document like this, so only the relevant part is apparent. The limit as x tends towards 2 from the left is coming in like this, and it looks like those heights get closer and closer to a height of 3. That means the limit down here is 3. Oh, that's the wrong pen. There we go. So ignoring this part of the graph, that's what the purpose was for that marker, really helps us see this kind of limit. But if you're one of those kinds of people that can just look at the graph, analyze all the features, and just run at it, if it's not too visually overwhelming, then that strategy probably isn't super valuable. But it's good to have options when you need it. So this one says we're approaching 2 from the right. That means everything in the left is once again irrelevant, but I'm probably going to need the horizontal axis still. That's height 3. We're approaching 2 from the right. That means we're coming in this direction. And it looks like the function values are just getting closer and closer to a height of 1 on this. So that tells us the limit on this is 1. So that's the 2 single-side limits here and here evaluated. Now that we've done those limits, this one can be a pretty tricky one. I think a lot of people might accidentally say 3 on this one because the solid dot is filled in right here, giving the function value 3. But that's just relative to f of 2. F of 2, when we evaluate it, we go to 2, go up to this point. The solid dot is the actual point on the graph. This value comes out as 3. But that's not the value of the limit. Anyone see what should go right here?
Isn't it that does not exist again?
No, they're not exist. Thanks for spotting that one, Nick. So we go D and E. We have to do this tedious chore right here and explain why, but it's based on the other values right here. The left-hand limit gave us an output of 3. The right-hand limit gave us an output of 1. So we just need to say the single-sided limits are not equal. That's what gives us a does not exist right away. But you know, a different way to look at this is just observe that the graph jumped down a whole bunch. This automatically would give us, from this portion right here, a does not exist. Well, that's always kind of great in a way. There's lots of ways to analyze this. But when we said the single side limits are not equal, we were referring to these values here being unequal. If you went that route and just look at these values, that's a great way to analyze it as well. Now, I'd say this one is pretty tricky. We're next taking the limit as x tends towards 4. Notice there's a problem at 4. No function value is actually plugged in, but that's all right because all we care about is, are the values going to be the same as we come in from the left? Looks like that's coming up to a height of 4 from the left. Come in from the right, it's moving up. Looks like it exceeds 4, but comes back down. So this limit would have 4 for the double-sided limit here. It looks like there's a match on the left side and the right side limit. But what would you all say to f of 4 on this problem?
Does not exist.
Yep, good call, Sean. This one is it does not exist because there's, well, no point on the graph whatsoever. If something was filled in, let's just pretend for just a moment, there's a solid dot right here, we would say f of 4 equals 1. But absent of any point whatsoever on the graph now tells us, you can say does not exist, undefined, anything along those lines, 4 not in the domain of f. I think a lot of times people would say undefined, which is synonymous with does not exist. I would assume WebAssign is going more often than not for undefined when it comes to a function value. It does not exist when it comes to a limit. But again, they're synonymous. You could have said undefined right here on a quiz problem, and that's also totally correct. But we did it, folks. This is a typical kind of example, just analyzing what the limits are saying purely through the graph. Yeah, go ahead.
So we'll always get a graph with these kind of questions, is that right?
Not always, but for section 2.3, yes, absolutely.
Do we use like a graphing calculator and then it graphs it for us? Is that how that works?
What we're going to do in section 2.4 is not using a graphic calculator, but instead, in section 2.4, we're taking these things. Instead of saying limit x goes to infinity, we'll say limit x goes to 5 or limit x goes to a. All these limit laws can then be brought into section 2.4, and we'll use those laws to calculate this kind of limit, not with this strategy, but it's going to be that same kind of idea. So we're seeing how it works in the graph so that when we go to get these values like we did here analytically, there's a connection in our mind on what we actually calculated, what it looks like visually. Other questions at the moment? Okay, maybe just a preview, since that is an interesting question. How do we do this if there's no graph provided? Let's turn backwards, give a little bit better of answer to that, and do this limit, pretending there is no graph whatsoever. So let's think of this one as a preview to section 2.4, only because this is a very interesting question asked in class. Thanks for asking that one. If we take this limit right here, this is what the work would look like. Limit x tends towards 1 of x squared minus 1 divided by x minus 1. In section 2.4, what we're trying to use is a property called direct substitution, where we're trying to plug 1 inside right here. We can't do that right away because, as we mentioned, plugging in a 1 in the numerator gives us a 0, 1 in the denominator gives us a 0, and 0 over 0 is undefined. So the limit can't be calculated in that way. The limit's defined, but 0 over 0 is undefined. In fact, we know the limit's defined. We said it was 2. So what we do instead is a bit of algebra. We take the limit as x approaches 1. First factor the numerator. This becomes x plus 1 times x minus 1. Divide by x minus 1. And now we're doing something kind of crazy algebraically. We do a full-on cancellation here. We write equals lim as x tends towards 1 of just now x plus 1. And this equal quality is actually valid, despite the fact the original function x squared minus 1 divided by x minus 1 and our current function x plus 1, they are actually totally different functions. Peeking at the graphs, here's how they differ. One's undefined at 1, The other, when you do that cancellation, defined it at 1 right here. Now coming back down, doing this algebraically, you can plug a 1 inside this. No undefined comes out, and it turns into 1 plus 1 equals 2. So that's pretty much how we're going to do this all in section 2.4, combining with the limit laws we saw before for the limit at finite values. And in this way, we never even had to look at the graph whatsoever. Kind of strange in a way, it's just calling back to some old algebra from the past. But any questions, folks, about that or otherwise? Okay, we'll get back into these kinds of things in section 2.4. And that section 2.4 is pretty much you're going to be doing, again, problems that go about like this, but a different kind of strategy because we're not going to infinity. Takes a while to get there because the limits in section 2.3, I mean, just looking at that, they feel more technical than section 2.2. But let's go down to, let's see here, we got through this one. And this is going to be, looks like our last set of definitions for our class today. Let me kind of move that up so we can get them both in view. We've looked at these kind of values before, but it was in the context x goes to infinity, outputting an infinity, or x goes to a negative infinity, outputting either a positive or negative infinity in section 2.2. So the only difference this time is x is heading towards a finite number, giving us these kinds of values. So it says, this statement here means f of x can be made arbitrarily large. That's why we've got an infinity here, by taking x to be as closest to a as we'd like, but not equal to a. As before, the function value of a is irrelevant totally. That's always pretty weird to get used to. Let's highlight them both for the emphasis. And let's do the same as before, provide one big overall graph and look at some of these limits. Calling back to section 2.2, just for a moment, we always said in 2.2, if you find a value of a limit, oh, that's where we started today. If you find a value for a limit, what it really means is you found a horizontal asymptote right here. So these limits, when they exist, provided you a horizontal asymptote. Change it all around. If you're heading towards a finite number and you get an infinity, that's now a vertical asymptote this time. So this is best illustrated just by plugging in some vertical asymptotes. Let's put in one at -4. Equation of a vertical asymptote always goes as x equals, and then the x coordinate crossed on the x-axis, and maybe another one at 2. So this is the vertical asymptote by equation x is 2. We'll plot the function in blue, just to keep it the same as what we did before. And this is what my function is going to do. It cannot even touch a vertical asymptote. Our functions can cross horizontal asymptotes, but not vertical ones. These are real strong barriers to the function. So I'm going to draw it in this way. The arrowheads are just my way of conveying it's going down as further and further as you get closer and closer to -4. Then on this end, let me try again with that curve. Let's let it shoot upwards. And maybe just sort of damp out in that kind of way. So that's our function. There's a couple interesting limits to take a look at. We're interested where we get values of infinity or negative infinity. So let's start off with limit x tends towards -4 of f of x. On this one right here, because x tends towards -4, we're following the curve in this direction, and the function values are getting larger and larger, negative, just going down. Similarly, on the right-hand side, this is a double-sided limit, so we have to look at this direction. It's also getting arbitrarily large negative, so we say the whole thing is negative infinity. The function is just plunging downwards on the graph on either side. So from this part right here, that's where we get the value of that limit. And then likewise up here, where the function is blowing up, going up towards positive infinity, we say lim as x tends towards now +2 of f of x. This one equals infinity because of this part of the curve right here. And the moment you have these two values put out, that means vertical asymptotes also exist on your graph. So outputting an infinity at a finite value for x is synonymous now to vertical asymptotes, much like putting an infinity on your limit and outputting a finite number. That one is synonymous with horizontal asymptotes. So a lot of these problems that we're looking at, you can just think of as another way to convey when you have asymptotes in the problem on these definitions. Any questions at all, folks, with the definition so far? Okay, let's try this out in a problem that's similar to the homework next and go from there. So next concept, definition 6, is just a rephrase of what we said before. A way to define vertical asymptotes now is just to say a vertical asymptote exists if and only if one of these 6 different kind of limits comes up. The most important part is the right-hand sides are infinities, and the inputs x tends towards is always going to be a finite number a. It can't be a positive or negative infinity. But this is also conveying that you can take a limit as a goes to the left, a left side limit, or a right-hand side limit, and still get these infinities. And you can still get negative infinities on the single side limits here and here as well. So either one of these is conveying a vertical asymptote on your graph. We'll connect that thought with this graph right down here and compute some values on the limits, and looks like some vertical asymptotes as well. So another graph again, this is one overall graph, even though it has 1, 2, 3, 4 pieces, it's still all just one function, y equals f of x. Oh, excuse me, this is r of x. For no apparent reason, we're using the function r. Don't know what it would stand for. Hopefully not revenue, because it looks like it plummets occasionally. So let's give these a try. First one is the limit as x tends towards 2. Any volunteers for this limit here?
Yeah. Would it be negative infinity?
Yeah, absolutely. Good call, Sean. What we want to look at is where the 2 is. Here it is on the x-axis. On either side, we're plummeting downwards. So just like you said, negative infinity on that one. Same idea as x tends towards 5. Well, in this location of the graph, both sides of the curve go upward. So as before, we can say this one is positive infinity, just sort of the opposite of the prior limit. Any questions, folks, with either 2 of those? Okay, these ones get a little bit interesting. This is limit x tends towards -3. So we're in this location, but notice the curves, they don't agree. They are branching in different directions, depending on the side you're coming in from. This one says -3 from the left. So if we decide to use the note card trick, this is the portion of the graph that we care about. -3 from the left, the curve plummets downwards towards negative infinity. So we just throw in a negative infinity here. This one is same kind of limit, but now it's from the right-hand side. That means delete the whole left-hand side of the graph. It's irrelevant, or just cover it up. As we get closer and closer to -3, only coming in from the right-hand side, this one's tending towards positive infinity. So those are those values, those limits there. And now, just a small side-related comment. What would you all want to say if we said limit x tends towards just 3 now? That's not a question baked into this one, but it's a pretty interesting question on its own. It's tricky because look, the values are different here, negative infinity, positive infinity. So if you said does not exist, I would say that's the best answer on this one. DNE.
You mean -3?
Oh, sorry, yeah, -3 from the left, -3 from the right. Sorry about that. And oh, that one should have been a -3 as well. Thanks for spotting that one. Took me a minute to find where the error was. Usually that's hard if it's your own error. But yeah, good call on that one. From -3, that one does not exist. At 3, the limit would have existed. It looks like its value is about somewhere around here. So that limit doesn't exist. But you know what's also weird about these things? That limit doesn't exist either. Nor does this one, nor this one, nor this one. These are just special ways to say the way the limit failed to exist. So every one of these, let's just say it this way, every limit here does not exist. All of those limits, but we can't say DNE on every single one of these because putting a negative infinity gives us a bit more of extra information on the way it fails to exist. So let's say here, we can't say DNE does not exist on these because again, we have to show the way it doesn't exist. But for this one, where there's a mismatch, it's either positive infinity if you come in from the right, negative infinity as you come in from the left. This is a good one to just say does not exist overall because the behavior on how it fails to exist totally depends on the direction you approach -3 from. Well, last thing we have to do is just say the equations of the vertical asymptotes. But every time we put out an infinity, we have an equation. Could literally go to this part. Let's actually do it this way by highlighting. This part right here is essentially your vertical asymptote equation, but it has to be written in like this, x equals 2. This one, we would say x equals 5. And if this one exists, we would say x equals -3. If this one wasn't even in the picture, this still implies -3 is now a vertical asymptote. We don't have to write it in twice, so it only needs to be put in one single time. So those are the vertical asymptotes of the function. And looks like we did it, folks. That's dealing with limits at finite numbers, giving infinite outputs, weird ways they fail to exist, in other words. Any last questions at all, folks, on example 4? Okay, well, with what we've got going on in the rest of these notes, looks like just an application. Instead of trying to race through this in about 3 minutes and some change, we'll leave this when we come back from on Tuesday's class, refresh some of the comments we took a look at, hit this application, but then we'll be in section 2.4 pretty shortly, where we're essentially going to be doing these sort of strategies to evaluate our limits. Don't forget about the graphs. They're giving us the information of what you actually calculated once you get an output. I'd say as far as the homework goes, if you decide to take a look at section 2.3, the application is the only one we haven't gotten to, which you could wait for later. So at the moment, working through section 2.2 will get you caught up. And working in 2.3 is just getting you a little bit ahead of the class before we come back on Tuesday. Well, any last questions at all, folks, before we call it a weekend?
I just have one quick question. Do you think you could go to the second example we looked at?
Yeah, absolutely. There's so many.
Okay,
Oh, there
yeah.
we go.
This is like kind of theoretical, just make so I can understand it a little bit more. For the first graph, could you logistically say like f of 0 just equals 1?
Yeah, absolutely. So that would be
Okay.
this point right here. And same with all the other graphs here to here.
Okay, I was just a little bit confused. Help me understand it a little bit more.
Yeah, so what we'd be doing here is inputting the value of 0 on the axis, going up here till we hit the curve, and the output is the 1, like you said.
Okay.
Well, thanks for asking about that one. Any other questions so far? Okay, well, have a great weekend, folks. Any questions come up? Or if you're working in the homework system and you see something weird, or if they're not accepting your answers, again, don't hesitate to hit the Ask My Teacher button. I'll be very happy to help out. I don't think I've gotten any questions just yet. That's good in a way, but keep in mind, you can't overwhelm me on these questions, even if you have a lot of them. Even if you're working at 3 a.m. on Saturday and you're clicking that button a lot, that's always totally fine. But have a great weekend. I'll see you all next Tuesday.
Do you have a question? Part of the full class with it. What we were talking before, would you go down real quick to
This one here?
No, a little further down. So right there,
Gotcha.
you said that these problems, so these types of problems will come with the graph, but sometimes they won't. These ones right here.
These ones would always come with the graph.
Okay,
Yeah,
yeah.
sorry for the miscommunication.
No, I just couldn't figure out how to ask it, because I was kind of confused how we would figure out like F4, for example, without a graph, but.
Yeah. Yeah, if it just says f of x right here, then the graph would definitely exist.
Okay,
Otherwise, if it's something like that right there, then you can assume there is no graph and we're doing it algebraically in that case.